So yes, thank you for that introduction. And I'm in a very privileged position as a physicist in that practically everyone has heard of my experiment. I guess you guys have, since you're here. It's not a very randomly selected audience, but it's even true of most taxi drivers that I speak to, or my mum. It's amazing. There are not many physicists that can say that their experiment has been in the national news and has somehow entered the public consciousness in a way that science rarely does, and I hope the science does more often, actually. So what I want to do with these 40 minutes is just try to explain to you what the endeavour is, but in particular explain enough of the physics that you can see maybe why we're so excited about these weird-looking plots that appear every now and then in a confused news item. So there will be quite a bit of actual physics in here. I'm not going to just show you lots of pictures of big kit, although we do have those, of course. And here's the biggest bit of it. Until the end of this month, is it possible to take the light? Is that okay? Is it possible to take the lights down in front of the... I can do that, I guess, can't I? That might be better. Okay, so for the last 2 years, finishing at the end of September, actually, I had a kind of management role at CERN. And so I was going, although my family were here and I was teaching here occasionally, I was flying back and forth to Geneva the whole time. And this is the view I used to get. So on this here, this is Mont Blanc in the background. This is Lake Geneva. This is Geneva Airport, where I'd either be heading to or from. And this yellow thing on the ground here, which of course isn't entirely visible from the aeroplane, is the path of the Large Hadron Collider. It's 27 kilometers around, and for a London audience, it's a very handy number and a very handy color, because it's almost exactly the same length as a circle line, and it's the right color, luckily. And also, you can see on here, there are these little things, CMS, LHCb, Atlas, and Alice. So what's going on in this tunnel is that the two beams of protons, the highest energy particle beams ever achieved in a lab, are being sent around this thing in opposite directions and collided head-on. The beams are a fraction of the thickness of a human hair. They collide head-on. And they collide in each of those 4 points, which are essentially, they're the detectors, which are there to record what happens when these protons collide with each other, which is the whole point of the endeavour. And one last London in-joke is that we built a lot of Atlas here at UCL, and Imperial built quite a lot of CMS. And they're about the right distance on the circle line as well, if you see. And you can also see that Bloomsbury is much more interesting than South Kensington. So because this is the main site of CERN, actually. Atlas is right near. In fact, if you look, this dotted line here is the Swiss-French border, and Atlas is the only experiment that's actually in Switzerland. The main lab of CERN is in Switzerland, but most of the Large Hadron Collider route is actually in France, in the Pays de Gex. Okay, so that's where we are. One question, one bit of physics which often comes up, and I like, is why is it so big? Why does it have to be so big? And okay, it's so big because we want to go to high energies, and I will try and explain more about why high energies are interesting in a moment. But the connection of why does it have to be big to go to high energies is not, it doesn't look that obvious on the face of it, but in fact, you can do it with Newtonian mechanics. So you know that a particle will carry on in a straight line unless acted on by a force, okay? These are the fastest moving, highest momentum particles we've ever had in a lab. Imagine the force it takes to make them bend and come round again and collide with each other head on. That's the limiting factor on the energy. It's how much, so it's not how much energy you can pump in. It's actually how strong can your magnets, your bending magnets be to make the thing go in a circle rather than as Newton would have it in a straight line, which is what particles like to do in physics. And that set, so the bigger the radius, the shallower the curve, the less powerful the magnet has to be, and in the end, the higher energy you can get to for a given power of magnet. And in fact, you might remember in 2008, we turned on in a great fanfare and then blew it up. It broke, and 9 days later it blew up, or an eighth of it blew up. Okay, it was an uncontrolled release of liquid helium. It blew up. It took a year. It was a big setback. It took us a year, and we're still actually not running at full energy. We'll shut down again at the beginning of next year and go up to full energy after that. But the thing that broke was actually these magnets. That's where the critical engineering factor is. These magnets have to carry enormous currents, and there was a problem with one of the superconducting magnets. I think, you know, with hindsight, we benefited from that year. We learned a lot more about how we do the physics, and that's one of the reasons the results have come out actually somewhat faster since we turned on than anyone else thought they might do. But also it's a useful reminder that while I will focus on us pushing the cutting edge of fundamental science, fundamental physics here, these machines do push the cutting edge of engineering as well, and they're very challenging to build, and there's a huge story to be told there as well, which I'm not qualified to tell because I'm a physicist, not an engineer, but the technologies involved really do push the edge as well. Okay, but back to the physics. This is the standard model in Lego or something. And I'm not going to spend much time on this now, except to say that these are the things in the universe that we know are not made of anything else. Okay, these are when we say fundamental particles. Fundamental physics is a phrase often annoys other scientists because what's so fundamental? It sounds like we're giving ourselves airs. It doesn't really. It's nothing particularly special about it, except that it is quite special that these are the only things in the universe that, as far as we know, are not made of anything else. In fact, you can turn that around and say everything we know of in the universe is made of this stuff. So what you've got here is the electron, neutrinos, which also get in the news occasionally, and up and down quarks, which are what sit inside the proton. And what we're doing is colliding essentially up and down quarks with each other. And then the whole pattern is repeated again. There's a heavier copy of the electron called the muon and another one called the tau. There are heavy versions of the quarks, strange, bottom, charm, and top. And they all interact with each other by swapping these guys amongst each other. This is the photon, which is light, electromagnetism. This is the gluon. Whoops, where's it gone? This is a gluon, which sticks the ups and downs inside the proton. You'll see that physicists don't try and make things too complicated, so the gluon, it does what it does, it glues things together. And then the W and the Z carry the weak force. And given what I've just said about the gluon, you can probably guess how strong the weak force is. Not very, it's quite weak. And the key, I'll come back to these occasionally, but the key issue that the LHC knew it could address was to do with the relationship of the photon, the Z, and the W, and how that ties us in with what mass is and how that ties us in with the unification of forces. And I'll come back to that towards the end of the lecture. So there we are, the Large Hadron Collider. And this is Atlas, this is the experiment that we built part of here at UCL. So what you see, this is the beam, comes in here, and another one in here, and they collide in the center here. And you can see that they're sort of surrounded by concentric cylinders of different technologies. So there are semiconductor trackers that detect the particles. There's a solenoidal magnetic field, and by how much that bends the particles, you can measure the momentum. This grey stuff here is called the calorimeter, and it's essentially mostly liquid argon. The bottom line is it has to be very dense, and it's supposed to stop everything it can. And as the things stop, they give off radiation, they give off photons, and you count the photons. It tells you how much energy. So all these are different technologies designed to work out what happens when two protons collide at these energies. You can see that it's pretty big. These are people here, in case you missed them, and there's some more down at the bottom here. These are European standard-sized people. And it really is huge. I mean, when going in there when it was being built, it was just amazing. Now it's kind of full, so you go underground and you see it, and all you see is lots of high-tech stuff filling a big space, but still looks pretty good. And one of the things that is maybe a bit surprising is that all this stuff on the outside, these big wheels here, all these toroids here, are designed to measure one kind of particle, which is the muon. It's a heavier copy of the electron, if you remember in the previous diagram. And we need a special detector to do it because the muon, because it's like an electron, it hardly interacts with the nucleus of the atoms in the liquid argon. And it's much heavier than the electrons in there, so it punches through them like a bullet through candy floss. But muons are especially interesting because you don't find many of them in nature. So if we've created muons, and you'll see that they were key in the discovery of the Higgs boson, in fact, we really need to know they're there. So what we have is essentially muon catchers around the edge here, which actually don't even stop the muon, but they tell us the track went through. So essentially any charged particle that gets through the calorimeter is a muon, and that's usually a sign that something interesting happened. This is, I said it looked quite good when it was empty. This is these orange toroid things here are the muon detector, the magnets associated with the muon detector. This whole space here is full now. This is one of the guys who was busy filling it at the time. This is a picture from 2005 when we were building the thing. It's kind of some enormous high-tech jigsaw with pieces built all over the world, including here. All had to come together, all had to work together, and all does, thank goodness. Also realized that something a bit special was happening with the kind of public engagement aspects or public interest in the experiment. When I saw this picture in the middle of FHM, I thought it was a bit odd. Not that I'm a subscriber to FHM, but someone showed it me. And this is how we look at the events themselves. So Well, this is a graphical representation of one of the collision events. You've got to imagine the beams coming in perpendicular to the screen and colliding in the plane of the screen here. And as I said, what's happened, so concentrate just on the big circular projection at the moment. What's happened here is two quarks or gluons inside the protons have bounced off each other. The quarks and gluons, they behave as though they're free, if you like, inside the proton, but they can never be separated from the proton. The force between quarks and gluons gets stronger as you pull them apart. So with a pair of magnets or electrical charges, the force gets weaker as you pull them apart, and it's a 1 over r squared potential. So you can, the further away they are, the less they interact. If you try and pull two quarks apart, it's more like pulling things on an elastic band or on a string, and the force gets stronger. And at some point, if you smash them hard enough, the string will snap, and what you get is more quarks and more gluons made by that energy release. And in the end, you end up with a whole pile of particles, a whole spray of hadrons here, which is what you see, these tracks. These are charged particle tracks. And you see the energy deposits in the calorimeter. And there are no muons. These are the muon chambers here. There are no muons in those events. And what you see here is just different projections of the same thing. The technical challenges are illustrated again by this. So the beam operates in bunches, so we have bunches of protons. Every 50 nanoseconds, there's a bunch of protons colliding with each other. And in those bunches, then, we don't get just one pair of protons colliding with each other. We get many. In fact, at the moment, we get something like 40 with the data that's going on now. In this, what this is a representation of a real event where you had about 12. Each one of these ellipses, you can see, hopefully, is a source of particle tracks. That means there was a pair of protons collided with each other there. And just to give you an idea of the scale, first of all, we have to pick out those. And this is an example of why the muon detectors are nice, because these two yellow ones here hit the muon chambers, so we know there were muons. And that's the collision of interest, really, in this event, because the most unusual thing happened there. All the other ones are events we've seen before, but that one's more interesting. So that's selecting that kind of thing on the way is difficult. And the other thing is that the speed of light is 1 foot per nanosecond. It's a number that particle physicists tend to remember, even though we work in metric mostly. And all the particles here are, to all intents and purposes, flying out at nearly the speed of light. And remember, the detector is about 50 meters across. So if you do this, and we have 50 nanoseconds, there's another bunch coming. So we have a collision comes in, everything heads off at 1 foot per nanosecond, but before it's got out of the detector, before it's got 50 feet away, and another one comes in. And so we've got these concentric rings of collisions coming all the time. All of that has to be time-stamped in the electronics. All the information has to be read out so that you put the right bit of data with the other right bits of data on the other side of the detector. And it's not just one coming at a time, it's now 12 on this picture, or 40. So the whole, you can see that the data processing and the readout, and it's farmed out around the world on a computing grid to try and make sense of it. A lot of it has to be done in real time. You do as much, obviously you write as much as you can to disk and spend a bit longer on it, but even then, the resources required are quite incredible. So, and we built, in UCL actually, we were responsible for a lot of the timing electronics that makes sure that the detector readout is in time with the collisions of the protons so you don't miss them all. Okay, so that's the machinery with what we're doing. What I want to do now is try and explain to you how to interpret some of the data that we're looking at on this. So essentially, to interpret the key plot that tells us that we found the Higgs boson, or a Higgs boson. And to do that, I want to talk about Feynman diagrams, and I confess there are 2 equations, but they're not that hard, I hope. So this is a Feynman diagram. Richard Feynman was a genius who invented quantum electrodynamics and drew cartoons about it that everyone thinks they can understand it. And actually, the cartoons are not just cartoons, they're real representations of the maths. So this is a representation of the actual quantum field theory calculation of an anti-electron coming in here and an electron coming in here, annihilating at this vertex to give a photon. And then the photon decays again to an anti-electron and an electron here. And this is an example of, in the tunnel that the Large Hadron Collider is in now, there was a machine called the Large Electron-Positron Collider, another example of inventive physicist names, which was colliding electrons and positrons, and it was large. So, and this is what it was doing. And there's a reason for it doing that. And the reason is connected, this is the first equation, you might have seen it before. Energy is equal to mass times the speed of light squared. Now, the speed of light is 3 times 10 to the 8 meters per second. It's a very big number. But if you have enough energy, E, you can make new particles of mass m as long as you have enough energy by a factor of c squared to do it. So if we use that to look at these diagrams, you can see that there's a bit of a problem, in fact, because we would have collided these guys at very high energy. So E is very large. Energy is conserved. So the energy of this photon has to be the same as the energy of the summed energy of these two. And the energy of these two at the end has to be the same as the energy put in. This energy is conserved. But there's a problem there because photons have no mass. So where's the energy gone in the middle here? You've got E equals mc squared. E has to be the same all the way, and it's large, it's not zero. But mc squared, if m is zero, sounds like it should be zero. And the answer to that is in the fact that these cartoons are actually representations of quantum mechanics, and this is the key concept of the talk, in terms of the physics. That we represent interactions by the exchange of virtual particles. And what virtual means is that it doesn't have to have the right mass. So it's one of those examples that in quantum mechanics you can cheat sometimes. Everything what's the phrase, everything that can happen will happen. Everything that can happen will happen at some level. There's some probability attached to that. And what happens in these kind of diagrams is all we can actually observe is what went in and what comes out. So everything in the middle is at some level a mathematical idea, a mathematical construct. But if you put the right ideas in, you get the right answer to a very high level of precision at the end. So there's some meaning to that. And the thing that you have to put in, which was the key concept of Feynman's QED, and also of the other theories that we use here, is this probability of the exchange in the middle is proportional to 1 minus q squared minus m squared. Now, in that, the q squared and the m squared, the q is the mass the photon has to have in order to make sure energy balances throughout the diagram. The m is the mass it really ought to have if it was a real photon, which is actually zero, because photons should have no mass. So you can see that this would just be 1 over q squared here, if in the case of the photon, and it means that the further away the photon has to be from its correct mass, the less likely this thing is to happen. So I said all that in words, but you can now understand one of the most important diagrams in physics, and I'll show you why in a second. When we collided this, first we collided it at 91 GeV inlet, and there was a reason for that, because there's a particle called the Z boson, which has a mass of 91 GeV over c squared. So if you do the sums, actually that can have exactly the mass it means to have in that diagram. So the 1 over q squared minus m squared would be 1 over 0, which is a very big number. Now, it's not infinity because there are other terms that come in, but it's still a very big number. And this allows you to understand, sorry about the effects there, what's going on. But this is one of the most important diagrams in physics, and not only is it important, one of the most important data sets in physics, and not only is it important, if you can understand this, then you will have no trouble understanding the discovery of the Higgs boson. So what you see here is, as a function of the energy of the electron and the positron that are annihilating, this is the energy here, central mass energy, the probability of the thing happening. So cross-section is just the number of times it happens, or the probability of it happening. And you can see the photon wants to have no mass. So and as you take the photon away and away and away from mass of 0, this probability drops like crazy. It's 1 over q squared. It's just going like that, 1 over q squared minus 0 squared that I had in the equation. But then as you get towards the Z boson, which wants to have a mass of 91 GeV, then you get an enhancement. It's a resonance, basically. You get a 1 over 0 kind of term comes in that's moderated by other things that you don't need to worry about, but stops it going to infinity. But there's a real peak there. And that's because the Z boson in the middle of this diagram can have the right mass. So the quantum mechanical probability of that thing happening becomes much enhanced, and that's the resonant phenomenon. That's what it means to discover a new particle. Because you've got a term in there where there's a new mass, which is the mass of the new particle, and it gives you this enhancement, this resonant enhancement. And we can do the same thing at the Large Hadron Collider. This bump here is the same thing. It's a Z, and this time it's a quark and an antiquark annihilating to give you a Z in the middle. And you can see that we can reach to much higher energies. That's why we built the Large Hadron Collider. We can go up to much, much higher energies than we had here. Here you see it stopping at about 120, or in the data it even stops before that. But here, it's going right up to 1,000, 2,000 even. And these bumps here, the little colourful ones, they're kind of the imaginings of theorists. What if there was a new particle there with a bump? And we're always looking at those to see if there is anything there. So far, nothing. You'd have heard about it if there was, not in this process. But of course, we'll get on to how we see evidence for the Higgs boson in a moment. Okay, so that's the key thing here, is this exchange of virtual particles. And if there's a new virtual particle with a given mass, you'll get a bump in your distribution at that mass. Okay, so back to this now. And as I said, the key thing here in this list of particles is the relationship between the photon and the W and the Z. And I want to show you another diagram, which is actually from my experiment as a PhD student in Hamburg. And this is another key data set in physics that you can understand with just the same principles that I showed you before. There's nothing new here. So what we were doing here was colliding electrons and protons with each other, so bouncing an electron off a proton. Most of the time when you bounce an electron off a proton, it swaps a photon, which has zero mass. And that's the blue stuff here. The line is the theory and the points are the data. So the electron comes in, smashes up the proton, but we don't really care about that. And the electron bounces off and we measure where it went. That's an electromagnetic interaction. It's a photon exchange. The red line on there, and the points, is when something else happens, is when it's a weak interaction and you swap a W boson. A W boson carries some charge. So when an electron swaps a W boson in bouncing off of the proton, the electron actually turns into a neutrino. And actually, we don't see that. It goes away. But we can measure the process. We can see how often it happens. And you can see here, this again, this is just the energy or the mass of the thing. And this is the probability of it happening. And you can see, again, that's why we call it the weak force. This is a logarithmic scale. It's many orders of magnitude in everyday life at relatively low energies. Many more orders of magnitude more likely to be an electromagnetic exchange, to exchange a photon, than it is to exchange a W, which is a weak exchange. But as you go up in energy, a slightly weird thing happens. Both of them are getting weaker, less likely, because higher energy is more difficult. But they're converging. They're coming together. And you can see around here, they converge. And there's a unification of the two forces there. What that's saying is that the energies, this is in the collisions we were doing in Hamburg back then, that at those energies, the weak force is actually wrongly named. It's no weaker than the electromagnetic force. In fact, it's the same strength. Those two forces have unified. And you can see that written on here, the unification here. Now, there are other unifications on here. There's, maybe the strong force unifies, maybe even gravity unifies, very ambitious. We don't know. That's speculation. There is evidence for some of it, but it's not experimentally known. But this is different. This is data. These points here are actually measured. They're not, the theory agrees with them, the theory is the lines, but the points are the data, and they're measured. This really happens. And, as you go back up and up in energy, in the end you get towards the energy of the Big Bang. But so let's be more workaday and just say, hey, we know two forces of nature here that unify. Why does that happen? Can we understand it? Well, you already know the answer. The answer is, that, in fact, the one key thing I haven't told you that you didn't know is that the W and the Z are heavy, and the photon has zero mass. W and the Z have a lot of mass. That already tells you why it's a lot easier to swap photons at low energy, because they're nearly at the right mass. They're zero mass. It's easy to swap a zero mass thing. As you go up in energy, the photon has to be further and further away from zero mass in order to conserve energy. The W and the Z are far away from that already here because they need a lot of mass, and it's very hard to create that mass. The energy needed to swap a W or a Z is a long way, is at very high energies. It's a long way away at this low energies. And that's the entire reason the weak force is weak. It's because it's difficult to swap a heavy object. The W and the Z are heavy. As you go up in energy, that fact becomes less and less important because there's so much energy around, you can make W's and Z's like nobody's business, just as easy as making a photon. And that's this unification. So this unification, and in fact the splitting, the fact that the W and the Z weak force and the electromagnetic force look very different at low energies, is due to the mass. It's due to the mass of the W and the Z. And that's where the Higgs comes in. So I'm not going to go through that slide because I can come back to it if there are questions. But, well, let me see. Yeah, I will do that. Sorry. This is solid state physics. So what we have in this initial diagram here, just to go back one, what we have here is a symmetry between the forces, which is broken in everyday life. Okay? So they're the same here. You can swap the weak and electromagnetic force for each other, and it makes very little difference to the whole physical system. But in everyday life, they're hugely different things. The weak force you hardly ever come across. It's beta decay. It's not much going on there. Whereas the electromagnetic force is ubiquitous. It's electricity and magnetism. So this symmetry that's there at high energies is completely broken at low energies. It's just not there in nature. Now, there was a Nobel Prize awarded in 1999 for Tuft and Veltman working out from the maths, that if you say that you absolutely need these symmetries to make the whole of the standard model of particle physics, the whole of quantum field theory doesn't work if these symmetries are broken. Now, that's a really big problem because obviously these symmetries are broken in everyday life. And in fact, what they proved was that massive particles break the symmetry. So you can't have a theory that works, on the one hand, with a broken symmetry, but as soon as you give any of the particles mass, you break the symmetry. And you can see there's a problem there because we know that particles have mass. So it just tells you you've got a great theory, but it's completely useless because it only describes massless particles. So the big excitement about the Higgs boson is that it allows us to bridge that gap. So what you do is you say, I'm going to introduce a field that fills the whole universe, quite a radical step, and I'm going to say that that field will break the symmetry at low energies, but the symmetry is still there at high energies. Now, I know that doesn't mean a huge amount at the moment, but it's a concept called hidden symmetry or spontaneous symmetry breaking. And the best example, which is the plot that I had here, actually comes from actual magnetism, from condensed matter physics, which is where some of these ideas came from in the first place. Electromagnetism is completely symmetric. It has no particular direction. It's spherically symmetric. So you can choose whichever axis to be your x-axis in a diagram you want. And that's this situation here. These are magnetic dipoles jiggling around at high energies. As you cool them down, they like to line up because that's a lower energy configuration. They could line up in any direction, but they like to be lining in the same direction. So there's a thing called the Curie temperature. If you heat some magnetic material, and as you cool it down, what had no net north and south poles, suddenly a north and south pole appear, and you've broken a symmetry. There was a spherical symmetry to the whole system, and suddenly you've picked a direction. You've got a north pole and a south pole. Do it a million times, the north pole and the south pole will be a different way every time, so the symmetry is sort of still there. But for a particular magnet, you've broken it completely. You've picked a north and a south pole. That's what the Higgs does for us. It says that at very high energies, the theory has all these symmetries there. Everything's massless, effectively. As you cool them down, they pick up mass, it breaks the symmetry. And that's exactly what's happening. So this is what would happen here in this diagram. Two of these guys would line up, and that would encourage a third to line up with them, and a fourth. If they're heated up again, there's so much energy, they disalign themselves again. But if you cool them down, in the end, they'll all line up in the same way. And that's the same physical process as to what's going on here, where the two forces are completely symmetric, but as you cool them down, the W and the Z go off in one direction, pick up mass, the photon doesn't and stays massless, and you end up breaking the symmetry between these two forces. So it's an analogy, but it's a proper mathematical physics analogy as to what's going on. And it's the Higgs field, it's the interactions with the Higgs field that actually do that. Okay, so in the last couple of minutes, just to show you the data then, what we do is we measure photons and muons. I said, for instance, in the detector, this is an example of a collision with two photons. These are photons leaving energy in the calorimeter here. No track pointing to it because the photon doesn't have any charge. And this is another plot, like the other two plots that I showed you, and this is one of the plots that caused all the fuss on July the 4th this year. So what you have along the bottom here is the mass. Don't worry about this bottom half of the plot here, but just look at this bit. You have the mass along here, the mass of the photon pair. Here you have the number of times it happened, and you see there's a bump here, and that bump is at 126 GeV or so, and that's the sign in the same way that the bump in the other plot was a sign there's a Z boson there. That's the sign that there's a Higgs boson there that wants to have a mass of 126 GeV, and you get an enhancement in the event rate at that point. So you can see that's kind of interesting. CMS, the other experiment, has the same thing in the same place. And we also looked at a different kind of event, which is these collisions. What you see here is a pair of electrons and a pair of muons coming off a collision, and that's because two Z bosons were produced. That's another way the Higgs is created and then decays very quickly. And one thing it can decay to is two photons that I showed you before. In this case, it's decayed to 4 leptons. And you can see here there's a bump as well. So these points of the data, this is what a Higgs would look like if it was 170, and you can see there's no sign of it in the data. Here, if it was 140, again, no sign of it in the data. Here, if it was 126, and the data is kind of up there. Marginal, but it's in exactly the same place as the other two plots, and also CMS have the same thing. This is the Z again, by the way. There's only a small number of particles. The same ones turn up all over the place. Here's a Z at 90 GeV, but this is the Higgs at 126 GeV. Again, and again, you know, the data got big error bars, not that much of it, but it's in the same place as the other three plots now that I've showed you. So there are 4 independent plots, all saying the same thing, that there's a new particle in the data, and that it has properties that are consistent with the Higgs boson. And that's just showing you that it's 6 sigma. If sigma mean anything to you, that's the significance of the result, that it's basically telling you that it's very unlikely to be just a fluctuation in the statistical noise. Oh, that's a zoom in of the same thing. So, I seem to actually have finished quicker than I expected now. I thought I was running out of time. So there's more time for questions, which is always good. Just to come back to the Higgs, though, what I said was that the interaction of the particles with this background field that fills the universe is what breaks the symmetry. It's what splits those two forces. It's what gives the W and the Z mass, and in fact everything else mass as well, but particularly in this context, the W and the Z. And it doesn't give mass to the photon, and that's how the symmetry is broken. And and we kind of knew that we would get an answer to that, because we knew, if you go back to this diagram here, where are we? If you go back to this plot from my thesis experiment, you can see I'm attached to it because I did my PhD on that experiment. If I can find it. So yeah, we knew that the LHC would be able to go way above this key energy scale. Okay, so we're not just doing a fishing expedition going to high energies. We knew that we could really study, not just get to this energy scale, which we'd done with the previous experiment, but go way above it and really understand what it was that was doing that. And just to, this may not be obvious, I talked about the field filling the universe and the interactions with that field giving things mass. How does that connect with a new particle that I call the Higgs boson? Well, if you've got a field filling the universe, how do you prove that it's there? If you're a fish swimming in water, how do you prove that you're in water? It's kind of everywhere. You haven't got anywhere without it to compare to, so you can't compare densities and masses and things. Well, one good way of doing that for the fish would be to shout, if they could, because a sound wave traveling through the water would be a sign that there was a medium between you. In space, no one can hear fish scream. The idea that if you can make a wave in the water, a sound wave underwater, for instance, that tells you that there's a medium there. It tells you there's a field there filling that space. Similarly, the fact that you can hear me tells us there's atmosphere in the room. The Higgs boson is essentially a wave in the background field of the universe. And it's the only way we have of proving that that background field is actually there. Because you could imagine, you could say, well, if the Higgs is everywhere and it gives everything mass, why is it so hard to see it? Well, the answer is, well, we could have other theories. That, you know, to postulate a field filling the universe is a bit of a bold thing to do. And in fact, when Peter Higgs sent his first paper off postulating this field, he got rejected because they said, well, anyone could say that. It explains the observed facts, but it doesn't make any new predictions. So, you know, it's basically useless. And he wrote back and said, well, fair point, but if this field is actually there, then you can make waves in it, and I'll call this the Higgs boson. He didn't quite do that, but he did add the boson in the second draft of the paper because of that. And it's that boson that is the testable consequence of the fact that this model of masses and symmetry breaking is anything to do with the way the universe works. And that's what we found on July the 4th, and I find it I'm still a little stunned that such a bunch of abstruse mathematical arguments lead to something as real as that bump in the data and what that means, which is the evidence that the Higgs field is there. Okay, so we're still digesting this as a physics community, although it's a bit odd because we've been sort of expecting it for a long time. On the other hand, to see it really happen in nature is entirely different from expecting it, which is of course why we build experiments, but it's worth knowing. Just to leave you with the thought that this is by far not the end of the story for the Large Hadron Collider. So it was built to do a bunch of things, to see how well the standard model works in this completely new regime of physics where these two forces are unified, where the Higgs boson lives in the wild. Why the W and Z have mass and the photon doesn't? Well, the Higgs is the reason. We need to sort that out now, and where that mass comes from. But we're still also searching for other things, other possible new particles and forces. Supersymmetry is a favorite. If anyone's heard of it, I can answer questions about it later. I'm quite cynical about it, I have to say, but there you go. Possible new dimensions of space. If they're curled up small, There are reasons that we wouldn't be able to see them except at high energy, and there are reasons that there's some problems that they solve with our standard model that are there. There are outstanding questions in particle physics that are not just to do with the Higgs. I mean, why are we all made of matter, not antimatter, for instance? Where did the antimatter go? Why are there 3 copies of all those particles in that diagram? As far as we know, there's no reason. There probably is a reason, but we just don't have the theory for it yet. And some of these things are postulated to solve some of those problems. The whole mini black hole quantum gravity thing is a possibility. It's become less likely now because we haven't seen any signs of it yet, but it still might be there when we go to higher energies. The main point is that we're doing physics for the first time ever in this fundamentally new regime, which is the regime above where those lines join. It's where those 2 forces are unified. It's where the Higgs boson is part of nature rather than being an unusual thing that you have to work hard to see. And we're now in the process of learning about the new particle we discovered and how do particles and forces in general behave in this completely new regime. So that's all. Questions?
Thank you. Very interesting. Have we any questions? We have one here.
You said the collider's not yet running at...
Hold on.
You said the collider's not yet running at full power. Are you expecting to find more things when it runs at full power? Are there things still not elucidated?
Yes. So, I mean, expecting may be a little strong. So the question was, do I need to repeat the question?
It's helpful if you do.
So the question was, do we expect to see other new particles when we nearly double the energy, actually? Expect may be a little strong, but certainly hope, and we will check very carefully. So there are if we found the Higgs boson and that's it, then there are outstanding questions, like, for instance, well, why is its mass where it is? All it does is allows things to have mass, but it doesn't predict them. And there are also other open questions. So we're hoping that we will get other clues and we'll find other new stuff. But there's no question like that we were guaranteed to answer the question, is the Higgs there or not? There's no guaranteed answer anymore. But there's a huge new bit of real estate in physics to explore, and we hope we'll find something.
Thank you. Any more questions? Yes, one here.
Hi. Where do you find the raw materials that you would actually send around the LHC? How do you isolate the material that you...
There's a bottle of hydrogen. there's a really cute video actually on the CERN website. It's got a journey of a proton or something if you want to have a look at it. But there is a bottle of hydrogen somewhere underground at CERN where, because hydrogen is just an electron and a proton, right? So I think actually what they do is they add another electron to it, and so it's an ion, and then they accelerate it, and then they strip both electrons off, and they push it away again, and then they send it into... On my aerial photograph, you saw there were smaller rings and that, so it goes through a linear accelerator, and then a whole bunch of smaller rings, and eventually goes up and up in energy every time, and eventually gets stuck in the LHC, and gets taken to the full energy. But it comes all from one bottle of hydrogen in the end. Yeah.
Any more questions? Yes, we have one here.
Should we take that one?
Are there any plans yet for what will come after the Large Hadron Collider?
Are there any plans?
Plans for the next
For what will
machine?
come after?
Yeah, for higher energy.
There are plans. Whether none of them are approved or agreed on yet, but there are various groups proposing things. The Japanese are very keen. Now we know what the Higgs is, you can build an electron-positron machine that can make loads of them as well. Because you couldn't do that before because you would have had to scan across a whole range of energies, but now you could. So there's a proposal to build what we call a Higgs factory in Japan, which would be a linear E plus E minus collider making Higgs bosons and study its properties in more precision and more detail there. That's about the only one that we really know how to do. There are lots of technological ideas, because obviously we don't have infinite budgets, and we've basically, the whole world works at CERN now, so we can't just collaborate with another planet and build an even bigger one. So, not yet anyway. So what we're trying to do, as always, is do more with the same amount or less money. And so there are umpteen ideas, some of which we're working on here, to achieve higher energies with better technology that costs less and doesn't need such a big tunnel, or can be done in the same tunnel but with better magnets and things. There's a whole strategy discussion going on now because, as I say, we're still absorbing the fact that we've actually found the thing. So it's interesting times, I would say.
Another question there.
Well, if we use the LHC, could we figure out through the Higgs field what would happen to antimatter subatomic particles, beams of them, when they interact with the Higgs field itself?
We know that they interact with the Higgs field, actually, yes. So, in fact, antimatter is not that exotic. We use it all the time at CERN. So, and we have studied it. So, and in fact, the machine that was in Chicago, the Tevatron, that was the highest energy machine until we turned on, was colliding antiprotons with protons and annihilating them. So we know that the mass of an antiproton is the same as the mass of a proton, for instance. So we know that the mass of an anti-electron is the same as the mass of an electron. And that mass is the interaction with the Higgs. So we know that that's the same. What we don't understand is why there's so much matter around and not much antimatter, because everything between them seems to be pretty much the same. So how did the universe end up to have loads of one and not much of the other? And that's an open question still. And one of the other experiments, LHCb, that I mentioned on the photograph but didn't have time to talk about, is studying that by looking at decays of matter and comparing them to decays of antimatter. But that is an open question. So we know that the interaction with the Higgs field is very much the same, at least to a very high degree of accuracy. But there are other things we don't understand. We certainly don't understand why there's so much matter and not much antimatter around.
Well, thank you very much. Unfortunately, we don't have time for any more questions, so I think you'd like to join me in thanking Professor Butterworth.
So thank you.